All right, let's hope the second time's a charm. This is I just redid the video that I did of this because I screwed up. And so this one will be better. And it's funny because I have these notes that I'm staring at, and I left myself a note from the last time I taught this that said rewrite these. And the reason I said to rewrite them is because I probably saw the same thing happen 2 years ago, but there's a big mistake here. So now I'm actually going to rewrite them. All right, so this week we're going to finish, or on this video, we're going to finish examining first order ODEs, okay, with a special case. So let's recall, if we have a first order ODE of this form, it's linear. And this is the best scenario because there's a solution with a very clear rubric. Right? So what we're going to look at today is this is a special case, and they're called Bernoulli equations. And as you'll see from homework, these things show up in the actual out there in the real world quite often, or at least they did in the past. And so Bernoulli was very into these equations, and he figured out a way to solve a certain kind of way. And here's what they look like. They're almost linear, is what I say. All right. So we have y times 2y plus py equals g y to the n, and where n is some real number, right? So it's just all we have is like a y squared or a y to the negative 2 sitting out here on the right. And these are called Bernoulli equations. And we're going to use Bernoulli's pretty cool trick to solve these. So we're going to go case by case. So case 1, because the solutions depend on n. So case 1, if n equals 0, we have, right, y to the 0 is 1, so we have y prime plus py equals g, and this is linear. So we know how to solve it, check. Okay, that's case 1. Case 2, that's where n is 1, okay? And if n is 1, we have y prime plus py equals gy. If you rewrite it, you get y prime equals g minus py, and lo and behold, this is separable, so we know how to solve it. Okay, so case 3. Case 3, we're going to assume that n is not equal to 0 or 1. In fact, let's say n is bigger than 1. Right. Okay, so we have y prime plus py equals gy to the n. Now here's the crux of today's matter. Okay. Bernoulli's first thought here was, well, I don't know how he thought it through, but this is how it works out. He thought, I'm just going to divide through the whole thing by y to the n. So I have y prime y to the minus n plus py 1 minus n. You got to do that exponential work. That equals g. And I guess he was staring at, I could make some funny thing up, but I guess he was staring at this and said, what happens if I do a change of variable and I let this thing equal v or v, right? So this is from Bernoulli. You let v be 1 minus n. Then v prime is 1 minus n y to the minus n times y prime, right? I just did the power rule with implicit. Okay, now we're going to sub this and this into star. Being very careful. So I'll leave the first term off. So straight away we have PV, because we've replaced y to the 1 minus n with v. Right. And if you look at this for a second, divide by 1 minus n, which is legal because n is not 1, then this guy is sitting right here. And so we have v prime over 1 minus n. And 1 minus n is just a number, 2, 7, pi, whatever. And this should be an equals. So the change of variable gives us a new ODE. And this one is linear. So you solve it using integrating factor. Voila. And this is where my notes went a little wonky. So let's just jump to the example. Okay, we're solving y prime plus 4 over ty equals t cubed y squared, and y1 is a half. So this is a IVP. Okay. Now notice this is y prime plus py equals gy to the n, right? So p is 4 over t, g is t cubed, and y to the n is y squared. So n equals 2. Okay, so following above, step 1, divide through the ODE times y squared. We get, I'm going to go back to white. We get y prime, y to the minus 2, plus 4 over t, y to the minus 1 equals t cubed. Okay, so now let v be y to the minus 1, which says v prime is minus y to the minus 2 times y prime. Right? And this fella, there we go. This fella is sitting right here with a negative out in front of it. So we sub. So this guy goes in here. Oops. Looks kind of cool. This guy goes in here. So now I have minus v prime plus 4 over 2v equals t cubed. Right? And this is linear. It's linear in v, or view now. So we solve it. Multiply through by minus 1 because we have to get it into standard form. Compute the integrating factor. Which turns out to be t to the minus 4. And then you write v t to the minus 4 equals the integral of t to the minus 4 times minus t cubed dt, which is equal to minus 1 over t dt which is minus the ln of t plus a constant. We can assume that t is positive because our initial condition has t being positive. Okay, now solve for v. And this is minus t to the fourth ln of t plus ct to the fourth. All right, so we found v, but we still need to define what y is, because that's what the solution is. And we let v equal y to the minus 1 in our beginning. So now this is 1 over y equals minus t to the fourth ln of t plus ct to the fourth. And solving, we get 1 over ct to the fourth minus t to the fourth ln of t. This is the general solution. Okay, so now let's find the specific solution, or the particular solution. Where is that? That's way up here. Y of 1 is a half, okay. So we have a half equals 1 over c. So c equals 2. Remember the ln of 1 is 0. Okay, so the particular solution is y is 1 over, I'm going to clean this up a little bit. There where we have solved the Bernoulli. Okay. I think for homework I assigned 3 of these. They're actually like an optional part of section 2.4. 28 through 30. And this is the second part of, I think it's homework 3? Yeah. And then homework 4 will be the redo, the second redoing of assessment 2 from Friday to Monday night. And that's going to happen every week, so just sort of get used to having Friday assessment, and then on Monday night, the form, alt form, is your homework. And that way you can see both forms and sort of clean up whatever you messed up on Friday for Monday night. And it'll help your grade a little bit.